Okay, cell potentials and concentration. So we've been talking about standard cell potentials, right? E with the 0 here. That's under standard conditions. That's where ion concentrations are 1 mole per liter. That's not always the case. But here we have zinc plus copper ions goes to zinc ions and copper, and the standard cell potential is 1.10 volts. What happens to the cell potential when the concentration changes? Concentrations change. So this is true when copper is 1 and zinc is 1. What if copper is 2 and zinc is 0.01? How's that going to affect that equation or that reaction? Is it going to want to go forward more or reverse? If we increase this concentration, is that going to make the forward reaction more likely or less likely? More likely, right? So more of this, and then here, if we reduce this, that's going to make the reverse reaction less likely, right? So the grid background here tells me that I'm supposed to write something here. No clues there. Under standard conditions, what would Q be for this? The reaction quotient. It's going to be the concentration of zinc divided by the concentration of Cu2+, which is 1/1. If we change the concentrations, and we have 0.01 divided by 2, now we have a reaction quotient of 0.005. The reaction quotient is going to go towards K. We could calculate what K is here from the cell potential. Delta E cell was, see if I can remember this, 0.592 over N times the base 10 log of K. What's N for this equation? 2. It's not obvious, but here Cu2+ going to copper, that's transferring 2 electrons, and the other one also transferring 2 electrons. So if we put those numbers in, oof. That seems a bit excessive. Yeah, I think I did something wrong. 1.1 times 2 divided by 0.0592. Yeah, 37.
I got that too.
Yeah. When I was going backwards, I did something wrong. So standard conditions, Q was 1, and it's going to move in the direction of becoming like K, right? So that means we're trying to increase the zinc ions and reduce the copper ion concentrations. So here, Q is less, right? So is that going to make the cell potential bigger or smaller? Bigger. You had a 50-50 chance. I don't think I'm explaining this very well at all, so let's just move on. So here we have an illustration of this same thing. So here we have 1 molar ion concentrations in each half cell, and here we've got 0.01 here and 2 there. This is going to have a higher voltage. Derive the relationship between standard cell potential and cell potential. Okay, we can do this. So we have 2 equations here that have delta G0 in them. So if we solve this one for delta G0, and then we can set these 2 equal to each other. Standard delta G is related to the standard cell potential. Delta G under non-standard conditions is related to the cell potential under non-spontaneous. So we've seen that guy before, right? That was equal to 0.0592 over n base 10, that's not base 10, base 10 log of q.
Wouldn't it be negative?
I'm subtracting this from both sides, and then everything's negative, so I made everything positive.
But no, I thought because of the original equation, it's negative RT ln, or negative. Wouldn't you be subtracting, right? Subtracting RT from E0 cell?
Well, let's just check the answer here. Yeah, it is negative. Okay. Ah, I went wrong way up at the beginning. This is equal to this minus that. So that messes everything else up. And, oops, you are very correct. That should be negative. Yeah, so this is all messed up in the middle. Great. That was just a waste of all of our time. Sorry about that. This equation has a name, the Nernst equation, named after a scientist. So the cell potential is equal to the standard cell potential minus 0.0592 volts over n base 10 log of q, where we've got cell potential in volts, standard cell potential in volts, moles of electrons being transferred, and the reaction quotient. And remember, the reaction quotient is calculated in the same way as the equilibrium constant, right? But it just doesn't need to be at equilibrium. Okay. Determine the cell potential of an electrochemical cell based on the following two half reactions. The standard potentials are on the next slide. And so here we've got nickel going to nickel, 2 plus, and we're given a molarity that's different than 1, right? And then the reduction one is here. Okay, so what are we looking for? Nickel to nickel 2 plus. This one's awkward because you have to show the whole stupid table. And it doesn't fit on one screen very well. Oh, looking on the wrong side. Nickel, nickel, nickel. Okay. Here is nickel. Okay. So nickel ion to nickel metal is negative 0.23. Oops. So lost now. Is this in the forward direction? The nickel one? Is it like it's written in the table? No, it's opposite. So that means that E0 for this is plus 0.23 volts. And then let's find this VO2 plus 1. okay, right here. So the VO2 plus to VO2 plus has a standard cell potential of 1. And this is the same direction. Oops. So the standard cell potential for this one is equal to 1 volt. So what's the standard cell potential for the overall reaction? We add them together. So we add those together, and standard cell potential then is 1.23 volts. But we want the cell potential. This is the standard cell potential. We're going to use the Nernst equation. So E cell is equal to E cell 0 minus 0.0592 over N log of Q. How do we calculate Q for this? We need the whole equation, don't we? So let's move this out of the way. This has 2 electrons, and this only has 1 electron. So I need to multiply this second equation by 2. And then I can add them together. And the 2 electrons are going to cancel out. So I'm going to end up with nickel solid plus 2 VO2 plus 4 H plus to create Ni2 plus plus 2 VO2 plus 2 H2O liquid. They gave us the 2 half reactions. We need to put them together into one balanced redox reaction. So, we learned all the steps for that in section 0.2. But here, the first parts are done for us. We just need to make the number of electrons equal and add them together. I need this overall reaction so that I can know how to calculate Q. So for this equation, Q is going to equal the products. So nickel 2 plus, that has a coefficient of 1, so the exponent is 1, times VO 2 plus squared, because of this coefficient. The water doesn't show up because it's a liquid. And then we're dividing by nickel's a solid, so that doesn't come into it. And then we've got VO2 plus, not to be confused with VO2 plus, squared, and H plus, what's the power for H plus? 4. We can't do this without finding the balanced chemical equation for the overall reaction. So we got E0. Now we need Q and N. What's N? 2. N equals 2, because there's 2 electrons being transferred. And for Q, we can calculate this because they give us concentrations. So the nickel concentration was 2 molar, and the VO2 plus where'd you go? Over here, is also 2. And that one is squared. Divided by VO2 plus, which is 0.01, squared, and hydrogen ion is 1 to the 4th power. 2 times 2 squared divided by 0.010 squared, 80,000. Kind of a nice round number. Standard cell potential 1.23 minus 0.0592 volts over N is 2, times the log of Q, which is 80,000. Should probably put that in scientific notation, but whatever. 1.23 minus 0.0592 divided by 2 times the log of 80,000 plus 1.0849 is what the calculator is showing me. So plus 1.08 volts. Phew, it matches the number up there. There's a bunch of different skills combined in that problem, right? We have to know how to combine half reactions to make an overall balanced redox equation. We have to be able to calculate Q. We have to be able to calculate the standard cell potential. And then we need to use the Nernst equation. Yep, welcome to Chem 1B. Just pile it on. Anybody have any questions? So we'll stop here and pick that up next week.